Thank you, and thanks for the opportunity to present to this community what is more of a tool, so that we hope might be useful to many of you. So we've heard multiple times in these days how neural networks are very good, can be very effective, but they can be sometimes a bit tricky to train, and especially if one wants to do so in an effective way with a large data set and in a scaling way on large architectures or machines. So as just now we heard about sharing code, so we've decided that as we were doing the heavy work of interfacing with the working infrastructures like TensorFlow, we would do it for everybody and release an open source code where you can train neural networks. And so since most of this was developed in Trieste, and our project leader Emine is one of the developers of Espresso, we thought what goes well with Espresso, some cream maybe, and so this code is called Panna, which is cream in Italian, so we hope that we can make it even better. Now I will briefly present the features, and we've tried to make this as modular and as easy to use with just input files as possible, even though it's all written in Python and it's, the code is available, so you can modify it as you want. So the general structure, I don't really need to remind you how this neural network works, but just very briefly, of course, we will have some descriptors for the atomic environments, and we will feed it for now to the structure of a usual fully connected feed-forward neural network. Out of this, we can calculate properties for atoms. In case of energies, we calculate this quasi-energy, which can be summed and then compared to reference values to build our loss function. This gives us the training for total energies, but we can also use other properties. In the case of energies, of course, the benefit is that all of this is differentiable, and therefore we can also get forces, and we will see that we can use those. So the descriptors, for now we are supporting the Bell-Parnello kind of descriptors, and also a modification of those. But since the code is modular, as I will show, in principle other descriptors can be added, and as the community needs them, we will add them in our format, or you can also do it yourself because it's a very simple format. And as usual, we are talking about kind of radial binning and angular binning divided by species. So you end up with, in the end, a fixed size vector, which is the input to the neural network. After this, you go through the usual procedure. You have a certain number of hidden layer, and you have the standard structure of multiply the previous layer by a matrix, add some bias, and then pass through some nonlinear activation function, which you can choose. At the end of this, the cost will just be calculated with the difference from your ground truth, and then everything can be optimized through backpropagation. And this is the heavy part, and since Google did a lot of work into giving us a framework that can do so optimally, we have tried to make use of that in the best possible way, and the best possible way for sampling this through stochastic gradient descent. So now to go a bit to the structure of the code, as I said, we have something modular. The idea is that you start with your data from your ab initio code. Now, of course, we support for now the Quantum Espresso output, XYZ format, but anything else can be added. You can also do it yourself because our data initially is just in the format of a JSON, so it's very easy to write, or we can interact with you and try to find, write with you a parser for your output, and many more we will add. And then there is the first block, which is the calculator of the descriptor, which takes the input parameters. So you just run a code with a simple input file with all your parameters, and this gives you one file for each descriptor. But we know that this is not very effective, and therefore TensorFlow has its own internal structure, which are larger binary files that can be easily processed. Some queues can be formed and can easily extract examples and make all of this scale very well for large datasets on large machines. And therefore, we provide another utility to convert this into these files, which are the ones that really will go into production mode to obtain your model. And of course, the training is the main part of the code. So even here, we give you all of the hyperparameters. I will then briefly mention, but there is a lot of flexibility into what you want to train, what is the structure, what is the schedule of the training itself. And of course, there is a code that reads exactly the same files for cross-validation so that you can make sure that your network is where you want it. Also on the validation set, which takes, again, the same input format, so everything is consistent. At the end of this, you end up with a network model, which hopefully you can, either use with our evaluation code on new data, or export to some applications. And some of these exporters we already have written, and I will show you. So I will just highlight the features. I said it multiple times. You don't need to write a single line of code in principle to use this. So you can just run some Python scripts. The underlying structure of TensorFlow, of course, is based on C, so it's still very effective, and it scales very well on multiple architectures, CPU, multiple nodes, GPUs, even TPUs, if you have access to those. We have tried to interface in the best possible way with all of the tricks developed to make TensorFlow effective. So at first step, and especially the direction TensorFlow is going nowadays, tends to bring you a bit farther from the structure, which makes you lose some of the speed and of the efficiency of TensorFlow, and we've tried to really go deep in the details of it so that you don't have to do it. As I mentioned, all the data processing is, again, handled by multiple pieces of code with simple input files, so that you can pre-process anything that needs to be pre-processed, and you don't need to, for example, have this done at computation time. So when you do the training, you're only doing the training, and for example, if you're calculating forces, all of these derivatives of the G vectors, which are very heavy to calculate, are all calculated in the beginning, once and for all. Now, for what concerns the neural network itself, again, from the input files, from the get-go, you can describe different architectures. And what we have experienced ourselves is that it is very important how you define the architecture of your neural network. You might want to try different things. You might want to define different architectures for different species inside of your system, because not all environments are the same. Not everything needs the same degree of accuracy. Not everything needs the same number of parameters. So we allow you to define very easily the structure of your network, the trainability of your network, so you can decide that you want to freeze part of your network or the network of one of the species in case you want to refine maybe just a layer, do some transfer learning, or load the network from one species to another species. All of this can be done quite simply in our code. And then, of course, you can define the activations that you want to use, some forms of regularization. We've seen L1, L2, but also the clipping of the gradients. You can use different cost function, and you can define the learning schedule for your ADAM. So for example, you can do a quench training where you start from high temperature and you arrive smoothly at low temperature to get very well converged results. Also among the activation, I want to mention that we've been playing a bit with this radial basis function, which I think are quite interesting, because for a shallow network, they can give you a structure which is effectively equivalent to a kernel, Gaussian kernel method. So you can also try and train as a neural network something that looks a bit like a Gaussian kernel. So, and we will soon have some results on this, but this is already available in the code. As I was saying, forces, well, of course, can be predicted once you have the neural network. Everything is differentiable. But the most important part is that we've put a lot of effort into letting you train with the forces. And we've seen that this is very important because it really gives you a very smooth potential energy surface. If you think for any given point, when you have forces, you have a lot more parameters, and this really makes your training and your validation come much closer to each other. So it's very important, especially for small data sets. And this you can do, and in a rather effective way. As you're training, because TensorFlow has its own visualizer, which is called TensorBoard, and it just runs within a browser, you can, even as the training is running, see all of the parameters, all of the scalars, and all of the weights of the network as they are evolving, so you can easily debug what is going on in your training, and if something is going wrong, you can stop it right there, and you can restart it, or you can see, because from experience, we've seen that there are many things that can go wrong during the training, and it's very important to have all of these under control in a rather easy way to spot this as soon as possible. And as a last thing, once you have your model ready, you can export the model, and we already have an interface with LAMPS. So once you have trained your potential, you can have it directly run a molecular dynamics simulation within LAMPS. And we're also interfacing with OpenKim, that itself is an interface with many other codes, and more can be added as the community wants, so that these models can be really useful to you. So just to give you an idea of a sample input, these few lines might be enough for you to start a training. Once you have your data set, you just need to tell us where it is and where you want the training to happen, some data about logging, what are the species that you're using, the zeros of the species. So all of this is to try and make your models train faster so that you don't need to train the biases, you don't have strong gradients that can be problematic. And then when you train, what is the batch size that you want to use, the learning rate, or how it should scale, and how many steps you want to run, or you can just let it run because checkpoints are saved at any given time. So even if the scheduler kills your job, you can restart from wherever you want or from the middle of the training if something has happened in the middle of it. So all of this just works. And then, as I was saying, the default network, so the structure of the network is the structure of the input parameter, and architecture is as simple as defining something like this. So just the size of each hidden layer and the final layer, the trainability of each one of them, if they should be modified or not. But also, if you want to specify for a given species in the same way, exactly, you can just define a different architecture and, for example, different activations. If you want to try something like this, mix and match, everything just happens and gets converted to the TensorFlow proper format. As you're training, you can go to a browser and see something like this, which are just your visualization of, for example, how your cost is scaling, but also your cost per atom or the RMSE, also divided by species, because we've seen in some cases some species are not really training, or their standard deviation is not really moving, so they are just giving a constant output value because there are many parameters. All of these can be seen as you are training. And of course, the weights, you can see how they evolve. So you can see if your model has converged, if all of the weights have a strong gradient that brings them to some incorrect place. And again, we think that this is very useful when you want to do something ad hoc. So the main idea behind all of this is really that people should be able to train their own network, and especially if they have maybe small data sets, because not everybody has access to tens of millions of simulations and wants to create a network that works for everything. As we've seen, it's often beneficial to train a network ad hoc. So I will now show you some results, and some of these are just like benchmarks from the community, but also some of what we've tried to do by fiddling with the parameters, because with this code we find it very easy. So this is an example of the on the ANI dataset. So just in this case 100,000 molecules, and with the original quite large architecture, this trains very, very easily, and it gets to an RMSE which is compatible with the literature. So in this case, let's say that this works. In red is the training, and the dots here and later will always be the validation. So this we can train, but then we said, okay, how about a smaller dataset, and how about a smaller network? Can we try something different? So we tried to fiddle with the parameters, and we tried to see if we can get something of the same result, of a similar accuracy, by something smaller. And we have reduced as much as we could. So in the end, we found out that even with a shorter descriptor and a single hidden layer of 64 activations, this is enough to achieve basically the same RMSE invalidation. So, and even starting with a smaller data set of 10K molecules, this is much faster. And in case you only have access to this data, there are just fewer parameters, but it gets to the same result. And if you also want to run the molecular dynamics with this, having a smaller model is not only easier for training, but is also way more feasible in your molecular dynamics, which evaluating the neural network is faster than doing DFT, but still more expensive than some Lennard-Jones. So you want to have something rather small. The other thing, because we can mix and match these weights, is that we try to do some transfer learning. So we took this architecture, and then we recalculated the same molecules with a different potential. And so we tried to see if we could start from this network and get similar results, but much faster and with an even smaller data set. So we just had 1,000 molecules in this case, and with 1,000 molecules, if you try any structure, you tend to overfit right away. But we've seen that if we start from a descriptor, a network that is good for similar molecules with a different potential, what we can see is that very easily and very rapidly we can quench the system and just get to a good network for this new potential in a matter of really just minutes through this transfer learning. So this is something you might consider if you have a few data points, but you have another data set that has something similar, but not exactly the same. The descriptors are good, and you can also just retrain the last layer and use the previous descriptors, but change the parameters of the output so that you fit your new potential. After this, we've also tried with some other models. So we tried to move to not isolated molecules, but a molecular crystal. And we tried to, again, keep a small data set of just 1,000 glycine crystals. And so the training from scratch is, well, the training is here in pink, and the validation is here. So you see that because this data set is so small, you overfit. It's not a very bad result, but it's not good. And even if you try to retrain from the isolated molecules, you get still a bit of an overfit. What really helps is to add forces. So as you add forces, you see that not only your validation decreases, but also the distance between your training and validation gets much closer. And this is because the potential energy surface is defined much better in this case. So this training with forces and the retraining and the transfer learning really seem to work in our case for small network with small data set to get you to some good results. As last, as many people said, the guinea pig of this field, so silicon. These, of course, can also be trained. So this, well, was just a Stillager-Weber large cell of 200 atoms and just 1,000 examples. It fits to a very small value comparable to literature. But for example, this is a normal training on energies, but this can also be trained with forces. So if you think you have 200 atoms and the G's and the derivative of G's are really a huge input, and if you're just training at the end of your network, also with this strong reduction, strong compression of data, this can still train really well, and you can get then a potential, and we are now running molecular dynamics, and everything is smooth and seems to work. So this is more or less what we've done. Here is where you can find our code, and you can find ways to contact us if you want to access the code, to have new features. We are planning to implement new features. There are tutorials, there are examples, and we would like to hear some feedback. And we hope that you might want to use this with your espresso or whatever flavor of DFT you want to have in the morning, that you might want to add some panna. So thank you.
Questions or comments? Did you?
So I think this is relevant because we haven't really talked much about it during the workshop, and this might be the last chance to bring it up. What about hyperparameter optimization? Do you guys have a flavor of choice? Is there sort of a way? You've talked about twiddling, picking up hyperparameters.
Yeah, so for now, we don't have inside the code any hyperparameter optimization because within TensorFlow, it's rather complicated to try and achieve that. But because of the way that this is trained with simple input files, what we're planning to do is to create another code that can automate all of this pipeline, and then in principle, of course, it can run everything in parallel and do this. But within the code, no, this is not available at the moment.
Yeah, I guess just to follow up, it's kind of nice to see that you took the ANI data set and you get the essentially a little bit better accuracy with the smaller neural network. Mm-hmm. We try actually that. The reason we chose with the larger architecture actually is the generalization. If you try to use this potential with smaller neural network and run larger molecule, it actually sucks.
So this is also what we have seen, that so when we try to extend to 10 heavy atoms, of course this does not work. So this depends very much on what you want to do. So this is actually part of my take-home message, is that depending on what kind of system you want to work on, you might want to use this small network because they work very well on your given system. If you want to have something generalizable, then of course you need to have more parameters, and this is what other people have been doing.
Okay, any other questions?
This is actually a follow-up of the two previous questions. I mean, for what I understood, on the same training data, if you fit a small neural network, then you generalize worse than if you fit a more complex neural network with more parameters. So is that what you agree
I mean,
on?
the generalization, so this is trained on molecules up to 4 heavy atoms. And also what they have done is to show that if you train a large network, you can generalize to 10 heavy atoms.
Okay.
This
so
kind of generalization, so you need more data, and,
so
and this is reasonable.
On the same data,
but on the same, not on the same data, on the same family of data. So validation set that is not been seen in the training with 4 heavy atoms, you can still achieve very good accuracy with a small network. If you want to generalize to something totally different, like 10 heavy atoms, then of course there are more details, and in that case it becomes harder to generalize with such a small neural network. But again, it depends on what you're trying to do.
Okay. Any more questions? No? So could you please move on?